All right, hello. It's you again. Hi, and me. I'm here too. So we're going to pick back up where we left off from yesterday's video, from day one video, which was October 29th, for balancing chemical equations. So that's what we're gonna do. That's night chemistry, chemical equations 2. Good job. And let's get right to it. So this is where we left off. We just balanced these various equations right here. 16, 2, 16 and 8, 2 and 2, 1, 2, 3, 1, 3, 1, 5, 2, 1, 4. By the way, notice I didn't write any ones. That's okay. Ones are understood, but on some occurrences, on multiple choice questions, they will ask you to choose the correct coefficients that you plug in, and so it would just list the coefficients. Like for the first one, it would just list the answer choice that would be correct would be like 16, 1, 8, not 16, 8, or not 16, 0. There is an understood 1 there in front of the S8. Okay, so let's keep going. All right, so balancing equations helps us demonstrate chemical reactions. It's evident at this point. It also should be evident that that we balance it for a purpose as well. The purpose is that we balance it to demonstrate the law of conservation of matter and mass, because atoms which are made of mass, are made of matter, have mass, cannot be created nor destroyed. So we say that the reaction must be balanced to demonstrate this. Notice here the chemical reaction. We have an H2 and a Cl2. Remember, those are diatomic molecules. Hahn-Cliff-Bratt, or Hahn and all the halogens. And that reforms to make two HCl's. If you were just to straight up write this equation out, you'd say H2 plus Cl2 yields HCl. But that wouldn't be balanced, nor would that be demonstrating the law of conservation of mass. So we actually have to put that 2 in there and understand there's 1 and 1 of each H2 and Cl2 in order to make this reaction happen. Now notice reactions also are the most reduced form. So if you ever get numbers that are all divisible by the same thing, they can reduce, just like a fraction can reduce, just like subscripts could reduce in the naming bonding situation. So this was actually a practice we did on the, for sort of a remediation type of thing. This one is not great for us, but if you, because we skipped over it, but if you did the first 10 slides on the Google Slides or what have you with the balancing sandwiches exhibition, then you can certainly go look at that. These as well, because that kind of wraps it up. These also don't reduce like they ought to because it's a little bit of a simulation. Anyway, so let's just move right on. There are 5 basic types of reactions. We went over this in yesterday's video and yesterday in class. Those 5 types of reactions, we went over. This was October 29th, and then of course there'll be another day in the future later on. But the day before this, we went over 5 types of reactions in our notes page. I won't pull that up right this minute, but the notes page that was given to you is a handout. We went over the 5 reactions. We have the synthesis. A and B form an AB compound. Then we have decomposition. If you have an AB compound that decomposes into an A and B 2 set species, not necessarily just one atom of each, but anyway, it just decomposes into at least 2 parts. Single replacement reactions is where you have a 2-part species and then a 1-part species that can either be an anion or a cation. And if it's an anion, it swaps places with the anion, with the anion of the other one, and the new reaction becomes its new anion, leaving the old anion on its own. Or vice versa, the cations can swap places and do the same situation with that. So let's keep going then. Then we have double replacement, is where you have a cation and an anion, cation, anion, or maybe I should do it opposite for you, cation, anion, and they swap partners. So that these 2 cations swap partners, so that this cation is with these respective anions, but this one's going to go get this one, and this one's going to go get this one. They swap partners. That's a double replacement or double displacement as it appears in your notes. And then combustion always involves a hydrocarbon, of course, with oxygen, burns, this is a burning reaction, and then releases CO2 and water every time. So Let's look at them a little bit more closely. The basic equation for synthesis is an A plus B yields AB. Two substances combine, you get one new compound. Pause and study if you like. Decomposition takes an AB compound and splits it into two parts. It could form new compounds afterward, where the A and B are also compounds. They're just smaller compounds, whereas AB would be the one larger compound. Nevertheless, pause and study if you like. Single replacement, once again, you have an A plus a BC yields an AC and a B, where A is the metal. So A is going to swap with the metal B. But if A is a nonmetal, then A is going to swap with the nonmetal C. Remember, nonmetal is always mentioned second in a chemical formula or in an ionic bond. One element replaces another in a compound. So we have Cu is alone. It's going to swap with the metal Ag, and Ag is going to become alone. Na is alone here. This is also written as like HOH, one of our strategies for solving this. So that Na is going to swap with the front H, become NaOH, leaving the front H by itself. Of course, diatomic, so it still needs to be H2, even though it didn't appear as H2 over here. It was HOH over here. It still needs to be H2 because if hydrogen is formed, it is always formed diatomic, just like all the other Hahn-Cliff-Brads. Double replacement, you have an AB plus CD reaction, forms an AD, that's metal with nonmetal, and a CB, which is once again metal with a nonmetal. It's like I said, it was 1, 1 plus a 2, 2 gives us a 1, 2, 1, 2, and a 2, 1, 2, 1. Pause and study if you like. Combustion always involves a hydrocarbon, CH. Also, the hydrocarbon can have an oxygen to it. It can be any organic compound. So it can be any combination of CX, HY, OZ, to be the subscript for O, or nothing in the oxygen or in that oxygen spot. Then you add oxygen, that just means it combusts, it burns in the presence of oxygen, forming CO2 and H2O. And oftentimes, whenever you see this in more legitimate fashion, you would see a triangle over the yield symbol, which means fire has occurred. This is some sort of explosive fire situation. Occur when hydrocarbon reacts with oxygen gas to burn. Here are two examples. Of course, they're already balanced. So this video shows similarly what is going on. And I will let it play. Synthesis. Double displacement. and combustion. Good job. Okay, so that's that. I'm going to need to actually reply to a message in a second, but that's okay. All right, so mixed review here. What type of reaction would this be? Pause, think about it, because here comes the answer. DR, double replacement, or DD, double displacement. What about this one? Oh, real quick, sorry. BA, CL, H, SO4, that's 4 different species. So that's an A, B, and a C, D, and they swap partners. That's why it's double replacement. What about this one? Pause and think about it. Consider. It is a combustion because you have a hydrocarbon, presence of oxygen, CO2, and water. Zinc, copper sulfate. What about this one? Pause and reconsider. It is a single replacement because you have a loner and then a 2-part species and they swap places, 2 metals. Then we have, let me move me for a second. So move me up here so I can still look at it the right way. This one combines, so it is a synthesis. Finally, last one, large compound that breaks into 2 parts. That would be decomposition. Good job. Let's keep going. What about 5 types of chemical reactions? The first thing is some notes on this. There are considered 5 types of chemical reactions, but I'm going to list more than that because there really are other ways to manage these terms. And some of the definitions are under ideal conditions, so understand that from the start, these are ideal definitions of what is an indicator, and they have specific definitions. So just understand that. There are varieties of scenarios that can come into play, but bottom line is understand what's going on. 5 signs. What are these? Think about chemical reactions real quick, like rusting, baking soda, and water, vinegar, added together, or sorry, baking soda plus vinegar, fireworks, etc. Think about what are some signs you think. Did you think about it? Pause if you didn't by now, and think about some you can come up with. And then we're going to define them now. So first we have to address what a chemical change is. It is when a substance changes into a different substance altogether. Examples like verb examples like this, like explode, rust, oxidize, corrode, tarnish, ferment, burn, rot. Pause and reconsider those if you need to. So the first evidence of a chemical reaction is that there's a production of a gas. Now, this isn't always something, but just because you see a bubble doesn't mean a reaction is occurring. But typically you have a gas forming that wasn't there before. A gas has been liberated due to the chemical change going on. Chemical change is just a less fancy word for chemical reaction or reaction. And so evidence of a reaction would be production of a gas. This usually involves an odor or bubbles, things like that to that extent. So make sure you're taking notes on these and give some examples like, a rotting food, breaking down of a substance into disappearing, not just dissolving, but disappearing into subparts and gases. Formation of a precipitate. So when you have 2 liquids that have dissolved solids in them, dissolved ionic compounds or salts, dissolved salts, not table salt. All ionic compounds can also be called salts. When you mix them together, sometimes they create a reaction of the 2 salts would rather react together, and then they'll undissolve, leave somewhat of an aqueous dissolved salt, and then create a brand new salt that's too heavy to be dissolved. That too heavy dissolved solid forms a precipitate and settles down to the bottom. That's what you see here acting in this. We're actually going to try to demonstrate this as well. This is kind of evident a lot of times, but formation of a precipitate is pretty typical of a chemical reaction. Make sure you get those notes. Emission of heat or absorption of heat. Emission means outward, absorption means inward. So it would either be emission or exothermic, and absorption or endothermic. Typically, if you have some sort of situation going on, you're going to have some sort of chemical reaction going on. Heat or sudden cold feelings exhibit these things. Once again, not always the case, but typically this is the case for a chemical change. So changing phases can also be related to this too, but this isn't, and phase changes are not chemical changes. So there are some exceptions, but for the most, this is a very specific definition as to when this can happen. Emission of energy, and this is generally light or sound, or both. They're accompanied together, typically together, but emission of some sort of energy is going to be evidence of a chemical change. Not always, but usually. And a different energy than heat. So heat energy was the last one. But heat can go in and out. You can't have light go in and out. You either have light or sound produced, or it's not produced. It doesn't. There's no anti-sound. Or there actually might be, but that's a theory unto itself. So we'll get into that later. Emission of energy, sound and light. Permanent color change. I put a little asterisk next to this because we're not talking about a color change like I put a marker on something and now we've changed the color. That's not a chemical change. We're talking about think about the color of cooked foods. They change color from batter to baked cake. Like they have a color change that's is the result of a chemical reaction. Rust and oxidizing, tarnishing is a color change that's a result of a chemical reaction with an oxidizer typically. So it's permanently there, or some of the compound has reduced down and become this oxidized form. The oxidized form is called rust or tarnish amount. So whenever you get rid of rust from something, you actually, there was like iron oxide, so rusty things, iron oxide. When you rub rust off, you're actually removing iron that was iron, got oxidized, and so those atoms of iron were removed from the iron, the pure iron, and it's going to reduce in mass because it became a new substance, and you pull it off, you wipe it off. So, that's the test thing, and that's the end of our notes, as you can tell. And then we just rehash the review, the stuff. We remember Hahn-Cliff-Bar. Really, the diatomic molecules are Hahn-Cliff-Brat. I need to go make sure that's changed. We do some more practicing, and this sheet gives you some names for compounds that you'll see that we have not talked about how to name them yet. Hydrochloric acid, HCl, sulfuric acid, H2SO4, ammonia, NH3. Remember that. Remember these because when you're doing the practice problems of balancing chemical equations and you have to take it from word form and into formula form, you're going to need to know some of these because they're not immediately evident yet. We don't know that, we haven't learned them yet. Look at the different types. Evolution is the other word, is gas form is called evolution, precipitation. We're going to be doing those 5 indicators lab and watch this occur. Wear our goggles, and that is it. That's all she wrote. So thank you for joining us today. This was another good little rendition. This is the end of Friday's lesson, or the end of day 2. And then we're going to preview some of those lab documents. Notice I've attached also online, I've attached the next practice page for balancing chemical equations, which is this on the front and this on the back. More practice to get better. The space is for you to write, the line is for you to tell the type of reaction, and that's user-friendly. And then we have the type of equations, the type of chemical reactions lab, which is actually going to come on likely Monday or Tuesday. So the next day 3, we'll call that just chemical reactions day 3. So be on the lookout for upcoming videos where I might highlight some more on this, maybe run some demos of this reactions. I actually owe you some demos if you've been at home for long enough for other purposes as well. This is going to be uploaded to the Google Classroom link that you're watching this video on. So have a great weekend. Work hard, ask me questions, text me, get with me, let me know what you need, and let's be problem solvers and not problem makers, troublemakers, and let's go dogs. How about that? Let's go dogs. We'll see you soon. This has been Night Chemistry, Chemical Equations, Balancing Chemical Equations, Day 2. Go dogs.